Okay, let's continue. So I'm going to describe an algorithm, an incremental algorithm, to compute the convex hull of a set of points in O(n) log n time. And we are going to also claim that this is a more robust algorithm than the O(n) cube algorithm. It's both more efficient and more robust. So this algorithm is called an incremental algorithm, meaning that we are going to compute the convex hull point by point. So the convex hull is going to be generated by inspecting the points, and we are going to generate each edge one by one in a certain order. Our goal is to, okay, if you find the first edge of this convex hull, then add the second edge of this convex hull, and then the third edge. And we are going to do this in an incremental fashion, and at the end we are going to have ourselves a convex polygon. In order to be able to do such an incremental algorithm, we need to first rearrange or organize the points we have. I mean, we cannot change their positions, of course, we're not allowed to do that, but we can have an order, a certain order of processing them. And this, therefore, I mean, this incremental algorithm, what it does is, it first sorts the given points on this 2D plane. It first sorts the points from left to right. Okay, so we are going to process the points in a certain order from left to right. And unfortunately, we see that when we process all the points from left to right, it's impossible to build this or construct this convex hull edges in a certain order, meaning that when I'm going left to right, I see that certain convex hull edges, if I'm going to do a clockwise order of these convex hull, for example, some convex hull edges which lie at the bottom we need to process these points from right to left. I mean, while you are going left to right, you cannot construct an edge which is this direction. If this is going to be an edge of the convex hull, while you are going from left to right, you cannot construct the whole convex hull at one shot from going left to right. So therefore, to solve this, our algorithm is going to do this. First, we are going to process all the points from left to right, and this is going to give us a part of the convex hull, which we call the upper hull. Okay? Then we process the same points from right to left. Okay? The whole set of points. I'm not going to distinguish the points I'm not going to separate the points saying that, okay, these are upper points or lower points. All points are going to be processed from left to right. But during this process, I'm going to be looking only at, and if you are going in a clockwise direction on a convex hull, you know that if you're on a convex hull edge, you always need to make a right turn. Okay, so we are going to be looking for right turns while we are moving along the edges of convex hull when we are going in clockwise direction. After I compute the upper hull, I'm going to process all the points again from right to left. So I'm going to use the reverse ordering of these points. Again, I'm going to be, since I'm always going clockwise direction, still when I'm going like this, if an edge is on the convex hull again, the next edge should make a right turn. It's always, I mean, if you are going in this direction, you are always making right turns on the convex hull. Whether you are going from left to right or right to left, this clockwise traversal of the convex hull gives you right turns. So in these two-phase algorithm, we will be computing the upper hull and the lower hull, and we can immediately combine them because the edge the upper hull ends, the lower hull is going to start at that same vertex. Okay, let me write the algorithm, the pseudocode of the algorithm on the board, but I forgot to mention some details of the algorithm, which is, during this construction, imagine we are at an intermediate point. We have computed the convex hull up to a certain point. for example, up to here, we have computed the convex hull. These two edges are in the convex hull. And what happens when we process a new point like this? For example, this is pi minus 1. This is pi. During this processing, actually, pi is here. This is pi plus 1. So when I'm processing from left to right, there can be a point like this, which appears at a very low place. And here you are going to look at this edge. Since you are processing points from left to right, you have no idea about what is coming next. You just, this algorithm is like an induction technique. You assume you have the convex hull, upper convex hull up to this point. If you are going to add the next point to this convex hull, what do you need to do? So if we add this pi to this convex hull, we just check whether this edge and this edge, the second edge here, makes a right turn compared to this direction. Okay, so this is that line. In order to have this edge, I'm making a right turn. Okay, so if you are making a right turn, this edge is always also going to be on the convex hull. Okay, we are going to see, it's obvious this is not going to be on the convex hull because you know the points that lie to the right. Okay, so now when we process pi plus 1, when we come to pi plus 1, what we see is that, here the extension is this. In order to have a right turn, the edge has to be somewhere here. Okay, this is the right turn edges. This edge here makes a very sharp, actually, left turn. It's almost like a U-turn. So, if I have such an edge, and don't forget, you are computing the upper hull, okay? What do you need to do in such cases? Which point is the point which which does not satisfy the convexity? So what do you need to do? In such cases, when you look, so what we did this check by looking at these three consecutive points. The edge between these pi minus 1 pi and the edge between pi plus pi and pi plus 1. These two edges, the second edge is making a left turn. So at this point, the point we don't want on the convex hull is the middle point. Okay, the middle point should not be on the convex hull. If we are making a left turn, it shouldn't be on the convex hull. So we remove this point in our current constructed convex hull. We say that okay, these two edges are not going to be on the convex hull. We remove these two edges, and then we say this edge should be on the convex hull. But wait a minute, we go one here again. If we consider this one, this was pi minus 2, we are still making a left turn. Okay, so remove pi minus 1 as well. So until you make a right turn, this is a right turn. Until you make a right turn, you remove all the points in between. If you add a new point, while you are not making a right turn, remove all the middle points going backwards on the convex hull. So while we are constructing the convex hull, so we are incrementally building edges on the convex hull, sometimes a point may say that, okay, remove the last two edges that you have put, okay, or remove the last three edges that you have put. So we are going to go back one by one until we find an edge that makes a right turn. And we need to also prove the correctness of this approach. Okay, how do we make sure we find at this point, if we do this, if we all make right turns, how do we make sure this part is convex, or in other words, at the end we are going to be computing the correct convex hull. So the proof of correctness is like this. So again, it's like proof by induction. We are going to imagine up to a certain point the convex hull is computed correctly, and then while we are adding a new point, the only way we are going to compute the correct convex hull, meaning that after we add this point and the edge on the convex hull, all the other points should lie below the upper hull. So the correctness criteria suggests that if you have the convex, if this is the upper hull, all the points have to lie below this upper hull. Okay, that's what the convex hull definition. So here, just assume, for example, we have computed an intermediate hull up to this point. So this is my convex hull. And I computed the convex hull up to this point, and I'm going to add a new point, for example, pi. This is pi, this is pi minus 1. Okay. Now, computing, I mean, the assumption that the convex hull up to pi minus 1 is computed correctly means that you know that this region is empty. Okay? You know that this region is empty. If you have computed the upper hull correctly up to that point, this region on top of the upper hull should be empty region. Now, when you add this pi, according to our algorithm, what we do is we add this edge to the hull. Okay, this is the edge that is going to be added to the hull, because these two other edges, they make left turns. Okay, since I described the algorithm that we need to make a right turn, we are going to see that this pi minus 1 and this point here are going to be removed, and our hull after we add pi is going to look like this. Our upper hull after adding pi is going to look like this. Now, the question is it possible to have a point on top of this hull? Okay, so if you can prove that there can be no point on top of this second hull I have drawn here, it shows that your algorithm works correctly. Okay, this is how you prove the correct. So if you can show that there can be no other point above this red hull, you show that your algorithm works correctly. Now, the only place that there can be a point above this hull is this vertical slab, this region. Okay, we already know that this is empty. Okay, so this part is empty. All this place is empty. The only place there can be a point between to invalidate the hull is this region. Okay, if this hull is invalid, what makes this hull invalid is the existence of a point in this region. If there's a point in this region, this hull, it means that we have computed the convex hull incorrectly. However, such a point can never exist, because if it existed, we would have processed it before pi. After pi minus 1, that point should, since we have sorted the points according to their x coordinates, okay, we know there is no point in this region. Okay, yes? Very good. So these are degeneracies that we need to handle. What if the 2 points have same x coordinates? For example, what if we have another point here with the same x coordinate? What are we going to do during sorting? So fortunately, this degeneracy is an easy degeneracy to handle. All we need to do is we need to decide on a certain ordering. like the lexicographic order. Saying lexicographic order of points means that after you look at their x coordinate, if they're equal, look at their y coordinate and then process them accordingly. So if, for example, smaller y coordinates, if they have the same x coordinates, smaller y coordinates are going to be processed earlier than that. And we see that, I mean, in that case, this would be pi minus 1. And since if we make a left turn like this, since this is going to be a left turn, we are going to remove this point at that region. So having the same x coordinate on the same line is not going to make any difference in our proof. Okay. So, I mean, we just showed that existence of such a point is impossible because of our ordering of these points. So the convex hull is computed. Also, we could have said that, I mean, the convex hull could be invalid if we had, for example, I mean, the only place that is going to invalidate the convex hull is the existence of a point here, and we showed that by ordering of these. Since we process them with certain order, that star point cannot exist. Okay, that region, the whole vertical slab between pi minus 1 and pi is empty. There are no other points. These are our event points. So that concludes our point. The convex hull is computed correctly up to a certain point. Now let me write the pseudocode of the algorithm on the board. Okay, so then we can discuss the time complexity as well. So we have proven the correct, but we haven't proven the correctness completely because, okay, this is the upper hull. What happens with the lower hull? We need to also discuss that, but it's going to be clear after I write the pseudocode of the algorithm. So the first step is sort the points by their x coordinates. If equal, y coordinates. Okay, I mean, or we can just say lexicographically, first by x, second by y coordinates. So we first sort the points. And if we try to analyze the algorithm complexity starting from now, we are going to see that the first step requires n log n time. If we are using a comparison-based sorting technique, we can use like merge sort, which is with guaranteed n log n time, to have the first step computed in n log n time. Now, the sorted points, let the sorted points be from left to right, P1 to Pn, okay? So the result of this sorting gives me points P1, Pn. Then, what we do is we first compute the upper hull, we name as L upper. Initially, it is empty, and we put P1 and P2. The first 2 points are put the upper hull directly. Initially, we put these points with P as the first point, P2 as the second point is put in the upper hull. Then we have a loop here for I is equal to 3 to n, starting from the third point. We do these things, put Pi on L upper. So we append our upper hull by putting the ith point directly, and also while the last 3 points, while our upper hull contains more than 2 points, and the last 3 points do not make a right turn, while the last 3 points do not make a right turn. delete middle point from delete middle from L upper. Okay, so for the remaining, starting from the third point, going all the way to the last point, we process all these points, and we look at the last three of them. If they don't make a right turn, we remove the middle point from our list, and we do this until the last 3 points on our L upper make a right turn. So it may be the case that we have put all the points here on our hull, but at one point here may cause to remove all the appended points one by one, so while we are going back on this while loop on the upper hull. Okay, so the second part of the algorithm, so this at the end of step 4, actually these are all different steps, so this is 5, 6, 7, 8. So at the end of these loops, what we have is that we have computed the upper hull correctly. Now what we do is, for the lower hull, we put n and pn, and we start with putting pn and pn minus 1 to the lower hull. Okay, we start the last point in the x coordinate and the point pn minus 1 to the lower hull. So we start from the rightmost point now. We store the last 2 points on the lower hull, and we now go in our loop backwards for I is equal to n minus 2 down to 1. We put pi to the lower hull, L lower, and we exactly have the same condition here. So this loop is, if the last 3 points on this lower hull do not make a right turn, again we are still trying, since we are doing in counterclockwise, even when we are computing the lower hull, we should be looking for right turns. So left turns are invalid in any case. So when you're traversing the convex hull, either it's lower or upper, it doesn't matter. If you're going clockwise, it means that you should always have right turns. Right turns are valid turns. And at the end, we have 2 structures, L upper and L lower, after these loops are done. What we do is we remove the first and last point from the lower hull, because these points are repeated. In other words, so it's going to be like this. I'm going to have an upper hull with these 2 points. I'm going to have a lower hull with the same 2 points. So in order to prevent this duplication, I remove the first and last points from my lower hull, and then I just combine these to avoid this duplication of the points. I remove them, and I append this lower hull to upper hull, and we call the resulting list our convex hull, and we are done. Okay, so this algorithm computes the upper hull. We proved that we compute the upper hull correctly. The proof can be extended very similarly to the lower hull to say that we are computing the lower hull correctly as well. And at the end, if we analyze the complexity of this, the first step is L log n time, and for n steps, so this for loop is executed n times, but we have a loop inside this for loop, so it seems like it's n squared at first sight. Okay, it's like you have a loop here, and you're potentially going over all the points again. What if you are removing all the points while you're if there are many points, many places you need to go back to remove the middle point while you are executing this for loop. But luckily, this step is only still on time, because when you remove a point from convex hull, you never process that again. So a point is removed from the convex hull only once. So the total, if you sum up how many times this while loop is executed, at most it's going to be executed n times. Okay? I mean, if you sum everything up within this for loop. So this for loop, its complexity is going to be on. Totally. The total complexity of this for loop is going to be on, because when you process, either you append a point to the convex hull or you remove it, and you do these things only once. You do not append you do not add a point to the convex hull more than once, or you do not remove it from the convex hull more than once. So each point is processed only once during these loops. Therefore, it has time complexity on. So the main factor in time complexity is the sorting of these points. So if you are given an already sorted set of points from left to right, you can compute their convex hulls in on time. In linear time, you can, if the points are already sorted, you can compute their convex hulls in linear time. Okay, so we proved the time complexity, and we proved the correctness, and we can say that the convex hull of a set of points in 2 dimensions can be computed in O(n) log n time using this algorithm. Now, in terms of degeneracies, what happens if, for example, 3 points are collinear? They're on the same point. Or one degeneracy was, as your friend suggested, what happens if 2 points have the same x coordinate? So if they have the same x coordinate, we can sort by their y coordinates. It's going to solve the problem. What happens if they are collinear? In other words, this algorithm is not complete yet. We said left turn or right turn, but what happens if it's not a left turn or a right turn? What if it just stays straightly on the line? So if 3 points are collinear, it means that this left-right turn test is going to return us 0. It's neither a left turn nor a right turn. So we need to decide what we are going to do in those situations. So, for example, what happens if pi minus 1 was here? Okay? Now, to be able to answer this question, whether should we remove pi minus 1 from our convex hull, or should we not remove it from our convex hull? It depends on what you're asked. I mean, if the question tells you output all the points that are on the convex hull, then you may have the pi minus 1 as a point on the convex hull, and you may want to report it. But if you say report the minimal number of points which define the convex hull, the edge is defined by actually pi minus 2 and pi. So this pi minus 1 is not required to define this edge of the convex hull. Then you can remove it in that regard. So, and if you decide to remove it, all you need to do is modify this while the last 3 points do not make a right turn. Yeah, and we will not even able to modify it actually. If it's not making a so this is not this pi minus 1 here is not making a right turn. It's either making a left turn or it's on the line. In both cases, we are going to remove this. So we don't need to make any modification to this algorithm if we want to remove pi minus 1. But if you want to retain it, then we need to modify this sentence so that the last 3 points do not make a, or we can just say the last 3 points make a left turn. Okay? If you just say, if it makes a left turn, remove it, otherwise do not remove it. Okay? So it's just an equality in the checks that you have. All right, so this concludes our first computational geometry problem, the convex hull, and how we develop an algorithm for that, and we proved its correctness. So we need to, so this proof of correctness is important. I mean, how you, this is the increment, we proved this by induction, by assuming convex hull is computed correctly up to a certain point, and adding a new point, the next point that is added, we compute the convex hull up to that point correctly using this algorithm. So the proof is, this time, is by induction. Now, any questions about convex hulls? During the break, one of your friends asked whether I'm going to give you the solutions of the homeworks. In the beginning of next lecture, next week, I'm going to solve the homework questions. So, because I need to also give you feedback about these homeworks. It's not like you did something, you need to know whether you did correct or whether your approach was correct. So what I want to do is, after reading your homework papers, maybe I will have an idea about alternative solutions. So, for example, if I solve the homework right now, you are going to say, okay, I did it like this, is it correct? Or I did it like this, there are many alternative solutions that may be correct. So next week, I'm going to look at all these alternative solutions which may be correct, and I'm going to give you an idea about alternative ways to solve or prove the questions as well. So I'm going to solve the homeworks at the beginning of next week's lecture. So if you don't have any questions, let's proceed with our next problem, which is line segment intersection. So we have finished this, okay. So I already motivated the problem at the beginning of previous hour, saying that line segment intersection problems may appear in GIS application, Geographic Information Systems application, in which each layer of information can be represented by a certain set of geometric primitives. For example, roads can be represented by line segments that are connected to each other. Some roads, dead-end roads, for example, may have line segments going nowhere. Okay, we may have dead-end roads, or we may have loops, in which we may have cycles in our line segment set. But whatever it is, any type of road map can be represented by a set of line segments. I mean, some of them, even you have curves. I mean, you may have a curved region, a curved road, for example. You can even approximate it by a set of smaller line segments to indicate the curve on the road. So some entities like roads and rivers, for example, may be represented by line segments. And a possible GIS query may be, give me or find me the bridges. Okay, I mean, in that problem, I mean, if a road is intersecting a river, I mean, the only way, I mean, if there's a road there like that, I mean, there has to be a bridge, like, right? I mean, either the river has to go under the road. Otherwise, I mean, not everyone has the 4x4 car. Okay, we are not going off. If your map does not contain off-road locations like some roads going in the rivers, you should have a bridge there. Okay, so if also our map contains large rivers, I mean, you have to have a bridge if a road is passing through a river. So one way to identify these bridges is to find the intersection between road line segments and bridge line segments. So it brings us to our problem: how do we compute the intersections between line segments efficiently? I mean, the problem description is very simple. I mean, given n line segments, our goal is, so we are going to be given line segments on plane like this. So in this instance, for example, I want to find out these two lines, these two, and these two. So I have three intersections at these points, and I want to find these intersections given these, how many, six lines. And one obvious approach, the naive approach, is just, it's not naive actually, it's the first thing that comes to mind is just test for intersection for every pair of line segments. If you have 6 lines, it's going to be 6 times 5 divided by 2, it's 15. So you are going to just 15 intersection tests to find these 3 intersections. This kind of an approach gives us an ON square solutions because we are conducting a test, line segment intersection test between each pair of line segments which are on the order of n square. Now, the question is, when we have this line segments becomes about, like for example, you have 1 million line segments, for example 10 to the 6 line segments, this approach is going to take this much time, okay, n square. So you need to spend, make this many on the order of this many intersections to find a solution. Now the question is, can we have a more efficient solution which is going to be more like on the orders of maybe 7 or 8, okay? Can I have like 10,000 times faster algorithm? It turns, I mean, from 10 to the 12 to 10 to the 8, it means that this algorithm runs 10,000 times faster than this n square algorithm when the number of line segments is 1 million. Okay, so I mean, if you're working in a company and you come to you say to your boss, say that I made this algorithm 10,000 times faster, that's a big achievement, right? I mean, so it's really important. I mean, and sometimes from going to n squared to n log n may achieve you this time speed up. Okay, so even the problem is very simple. Your solution is very easy to implement. Practically, you may have to wait like 1 hour to, in certain large problem instances, you may need to wait like half an hour or 30 minutes or 1 hour to get the set of intersections. Can you reduce it to 10 seconds, 20 seconds? I mean, which is reducing from 1 hour to 10 seconds is a big achievement. And our goal today is going to be this. Can we solve this line segment intersection problem in ON log n time? And the answer is going to be yes. We are going to see a plain sweep algorithm to do that. Okay, so first of all, the book assumes that, again, the primitive things are handled by computational geometry libraries like that. But first, let me ask you this. If I give you 2 line segments, how can you test whether they intersect or not? Did we talk about it in the first lecture? I think we talked about it, right? Any ideas? So how are we doing it? Just remind me. If I'm given 2 line segments, okay, I want to find this intersection point, this point, and first of all, I want to find whether they intersect or not. You can say we can use parametric line equations and find this here, but if you use parametric line equations, I mean, you are treating these as lines. For example, these 2, okay, these 2 line segments, they do not intersect, but their parametric line equations intersect. So how can you how can you say that, okay, these 2 intersect and these 2 do not intersect? What kind of a simple test can you have? For example, maybe you may not need to do even this complex line equation. I mean, you may skip finding this point if you immediately can know these 2 do not intersect. If you can have a more quicker test to find that these 2, their extents do not intersect, you may omit this test. So,
you can test if the other 2 points of the large
Okay, very good. So the test involves checking whether these two endpoints lies on the same side of this one. What about this? So here, this one does not intersect with this one because both of these points lies on the left side. But for this one, it doesn't intersect, but these points lie on the opposite sides. They lie on the opposite sides, but yes, exactly. And the answer is obvious. We need to do this check for both of these line segments by using both of them as reference line segments, in certain order. We need to see that in order to have an intersection, for both of these lines, these 2 points have to lie on the opposite sides. Okay? If these 2 line segments intersect, the 2 endpoints have to be on the opposite sides for this reference line segment, and for this reference line segment, the other endpoints also should lie on the opposite sides. Very good. Also, we can also do direct parametric line equation equality and check whether U, the intersection point U, is between 0 and 1. That's also a good solution. But maybe we should think about whether this check or the parametric line equation is going to be more efficient. I mean, we need to think about since we are going to be doing this a lot, we need to think about how many additions, multiplications the parametric line equation is going to need, and how many multiplications or additions this check is going to need. If this check is more efficient, maybe before finding out U, we can apply this check to see they're intersecting or not. And only if they intersect, then we can, to find the actual point of intersection, we can apply the parametric line equation test. So how do we find whether they lie on the same side or the other side? So we have the cross product to our help. And if we have these two-dimensional points, the cross product turns out to be a very simple thing actually. Like it's like we just multiply x1 minus x. I mean, the final equation is going to be a simple equation, and we just need to check the sign of that equation. To check whether a certain point lies to the left or right of a line segment. But again, we need to count how many multiplications or additions we need for that test, and how many multiplications or additions we need for the parametric line equation intersection test. We need to compare these two to see which one is more efficient. Let's do that actually right now. Okay, so I'm just wondering, I mean, my intuition is that this test is going to be cheaper because many people are using this test, the left-right test. I mean, if the parametric line equation is cheaper, then I don't know why people are using this test. They could directly use parametric line equation. So my intuition is this one should be cheaper, but I'm just, let's see what happens, okay? So given two line segments, x1, y1, x2, y2, and xa, ya, xb, yb. Okay, so we are given 4 points. And the parametric line equations are x is equal to x1 plus x2 minus x1 u, and y is equal to y1 plus y2 minus y1 u. And for the other line, x is equal to xa plus xb minus xa. What? Can I say u? No, we cannot say u. That if you are going to use all these 4 equations together, that u, that parameter, is the way you have traveled on that line segment. Okay. Here, you need to use a different variable. You cannot tie, I mean, this u is the parameter that ties the x-y relationship of this line segment. This u is different than the u you are going to use for the other line segment. So, for example, let's name it as v. Okay, we need to use a different variable for the other line segment if we are going to somehow try to merge these two. Ya plus yb minus yav. Now, if they intersect, at the end, both both u and v have to be between 0 and 1 if these two line segments intersect. Okay, and it's not enough to have u between 0 and 1. V also has to be between 0 and 1. So we need to make these, so if they intersect, x and y's are equal to each other, so we can directly make these equal to each other. So saying that xa plus xb minus xa plus, v, and ya plus yb minus ya plus v. So what we have here is are two equations with two unknowns. Okay, so we need to solve a system of equations here, two equations with two unknowns. Let's see. So u is going to be equal to, u is equal to ya plus yb minus ya v divided by y1 plus, minus y1. Okay, if I'm going to get u, so ya plus yb minus ya v minus y1 divided by y2 minus y1. Okay, so this is u, right? U in terms of the known parameters and v. So and then what I can do is I can write this, instead of this u here, I can write this. Okay, so x1 plus x2 minus x1 times this thing here, let me name it as E, okay? This is equation E1, okay? I mean this part, just I name it as E1, so this one times E1 equals xa plus xb minus xa v. So this E1 actually also has a v. Oh, okay, I need to write it to get v out of this, but I mean you probably have the idea it's going to be a lot of multiplications and additions to find what v is. And after that we need to also plug v here to find u, lots of multiplications and additions. So it is, I mean, I can imagine more than 10 multiplications and additions to solve for u or v. Now, for the other tests, let's see what we need to do again for the other test. xa, ya, xb, yb, y1, x1, y1, x2, y2. So in two dimensions, the cross product between, for example, the cross product between two vectors, xb minus xa and yb minus ya. Okay, so this is one vector. And to find out whether x2, y2 is to the left of it, I can form this vector. So cross product of this vector with x2 minus xa, y2 minus ya. So we need to compute this cross product and check the sign of it. Okay? And we are going to do this cross product 4 times for each point, querying each point whether it is lying. For example, we are going to do it for this one, and check whether these 2 points lie to the same side or to different sides on this line segment here. And we are going to do the same thing for taking this as reference and checking for these points. So this cross product is going to be computed 4 times, but let's see whether the cross product term is easy to compute. And one other advantage of this approach is that if in the first 2 tests you find that the 2 points lie on the same side, you don't need to do the second test, because during the test you can find out that the line segments do not intersect. Okay, so I mean, if these 2 points were lying here, after the first 2 cross products, you may immediately conclude that they are not intersecting. You don't need to go all the way to do the 4 intersections. However, for this approach, we need to go all the way to the end to compute u and v. And if we compute v and it turns out to be not between 0 and 1, again we can omit doing the same. This E1 computation can be omitted at the end if v turns out to be not between 0 and 1. Now, so the cross product I, j, k, I have xb minus xa, yb minus ya 0, and x2 minus xa, y2 minus ya 0. I know that I and j components are going to be 0 since I'm doing two-dimensional, computing the cross product of two-dimensional vectors. Their I and j components are going to be 0. The only component that is not 0 is going to be this. And the cross product is actually equal to xb minus xa times y2 minus ya minus x2 minus xa times yb minus ya. So in order to check whether a point lies to the left or right of a line segment, you need to do 2 multiplications and 1, 2, 3, 4, 5 subtractions. Okay, so five additions and 2 multiplications are enough to check. So at the end, this is going to give you the sign of this is going to give you whether that point is to the left or to the right. If this turns out to be 0, it is on the line, or on that line here. If it's what we did was we did this cross product, right? xb minus xa. So if it is greater than 0, it means it's to the left. If it's less than 0, it means it's to the right of this line segment. So 2 multiplications and 5 additions is enough to make this check. And we may need to do this for a total of this times 4. So it's 20 additions and 8 multiplications at most. Okay, so at most 20 and 8 multiplications. Maybe, I don't know, it may be comparable to, I mean, but this equation seems simpler to the solving systems. The systems of linear equations seems harder to me, at least. I mean, right, this formula is easier to implement as well. I mean, you just need to do this to check whether it lies to the left or right. Yes, yeah, exactly. This is, yeah. if you want to find out which point they intersected, you need to use the systems of linear equations. Okay, so we are going to use the parametric line equation solution to find at which point they intersect. But to find whether they intersect or not, this may be a simpler check to see whether they intersect or not. Now this is a geometric primitive test that we do. Given two line segments, do they intersect? Or if they intersect at which point? The book does not have a solution to this, but as I said, these line segment intersection, for example, they are readily available as functions in this, for example, in CEGAL library, the Computational Geometry Algorithms library. If you go to this library, you are going to have a function which takes 4 points and treats 2 of them as line segments and gives you this intersection test, okay? I mean, you don't need to implement these intersection tests from scratch by yourself most of the time, because these libraries do have these tests already implemented, and much more complicated tests. I mean, this line segment, there are tests like whether 2 convex polygons intersect or not, or whether a point intersects with some other complex object. So all these things are already implemented in libraries like that. So let's have a break.